Finally, in this lesson, we're looking at side-side-side triangle congruence. And if you think back to the last two triangle congruences, ASA was angle, side angle. Side angle, side was two sides and the included angle. This means if the three sides of one triangle are congruent to the three sides of another triangle, then my two triangles are going to be congruent. So they go through the process of constructing a triangle using a compass and a straight edge given the three lengths. Now, these measurements aren't accurate. In other words, this length on this paper isn't 4 inches, but I could try to construct a triangle just like this so that you know what that construction looks like. So remember that anytime you're constructing something new, you start with a blank segment. So I'm going to call this D, and from D, I'm going to duplicate the length of segment AB. So I'll call this E. And I would duplicate the length of BC at E. I would duplicate the length of AC at D, and notice that they intersect. So when I connect the dots, notice how I have a triangle that looks just like that one. Okay, so this is kind of demonstrating that side-side-side congruence actually works. So in this example, they're asking us to use rigid motions to show that one triangle is congruent to the other. Because remember, from 2 chapters ago, if we can perform a sequence of rigid motions to one figure to map it onto another, that was the first definition we had of congruent figures. So in example 1, they have these 2 triangles, and so they started by translating along this vector so that A would map over to D, and then they did a rotation so that AB would coincide with DE, and then they reflected triangle ACB over so that it would land on F. I'm going to skip going over this part B in the notes section of your text because it deals primarily with using rigid motions. And most of what we're interested in now in this module and moving forward as far as side, 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 side angle, side angle is using those properties to determine whether figures are congruent, using congruent figures to set up and solve equations, and then of course completing proofs with these properties. So I really want to get into that. So in this example 2 for explain 2, we're determining whether the triangles are congruent based on side, side, side. So in this problem, I know that this is 1.7 and so is this. I know that AC is 2.3, just like DF. And BC is 2.4, just like EF. So these triangles are congruent by side, side, side. Let's look at a similar example. DE equals GF, which is 20 centimeters. So segment DE is congruent to segment GF. DH is equal to FH, which is 12 centimeters. So DH is congruent to FH. Finally, EH equals GH, and they're both 24 centimeters, so that means EH is congruent to GH. So the 3 sides of triangle DEH are congruent to the 3 sides of triangle GH. So the two triangles are congruent by side, 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 triangle congruence. As I've mentioned before, a lot of the questions in this module basically boil down to, are the triangles congruent or not? And so in number 5, I have that PN is congruent to RS. Notice that they are the same length. PM is congruent to QS. Again, notice that they are the same length, but MN does not equal RQ. So the triangles are not congruent. In number 6, they didn't give us any lengths, but they did tell us that this length is equal to this length, and that this length is equal to this one, and we know that GH is congruent to itself. So yes, the triangles are congruent by side, side, side triangle congruence, because we noticed that GK, was congruent to GL. KJ was marked congruent to LJ, and GJ is congruent to itself by reflexive. Ridiculously short video, we're almost done. Once again, we're applying triangle congruence to algebra problems. So in this example, it says she has these triangular pendants and they're matching. So it's asking for what value of x can you use a triangle congruence theorem to show that the pendants are congruent. Now I know that AC and AB are equal to JK and JL. So that leaves BC, 4x minus 6, having to equal KL, which is 3x minus 4. And then they solved for x and found that x was 2. Similarly, in part B, we would notice that PQ is congruent to MN, and PR is congruent to MO because they have the same measure. So if NO is going to be congruent to QR, then triangle MNO would be congruent to triangle PQR by the side, side, side triangle congruence theorem, and the equation 3x minus 11 equal to 4 would have to be true. And so 3x would have to equal 15, and x would equal 5. In this last example, we have these two triangles. We have that this angle is 60 and this angle is 90. So we can use the triangle angle sum theorem to find the measure of angle H. The measure of angle H will equal 180 minus 60 plus 90. So that means that the measure of angle H is 30. Well, that's convenient. I have a 30-degree angle over here. And so if I have angle G is congruent to angle U, angle H is congruent to angle V, then in order for these triangles to be congruent, 8x minus 12 would have to equal 12. So 8x equals 24, and x would be 3. The question is asking us which triangle congruence theorem would we use? And, well, I have this angle congruent to this angle congruent to that one, and these sides between them, in other words, the included sides, I have set to be equal to each other. So this would be angle, side, angle. Now we haven't solved for y yet. Angle T would be congruent to angle F, so I would do 60 equals 7y plus 4, and that means that 56 equals 7y, and y is 8.